Let's talk about 4 uses of the normal distribution in econometrics and statistics. So we can use the normal distribution when we want to calculate the probability of a random variable falling in a certain range if we know that the variable is distributed following the normal distribution. We can use the normal distribution when we want to test hypotheses about a sample mean. We can use it when we want to test hypotheses of comparing two sample means to determine whether the hypothesis that the population mean of each one of the groups, if the population means are the same. And we can use it to test hypotheses about regression coefficients, which is going to be our main focus in Econ 41. So suppose we have a random variable, we'll call it x, that is normally distributed. So right now we're assuming it's normally distributed. This variable has a mean 200 and standard deviation 50. So we ask questions often like, what is the probability of drawing or observing a value of x less than 180? So that might be a question we might ask. What's the chance that this random variable will be less than 180? And we ask those kinds of questions every day in life. What's the chance that it will rain a lot tomorrow? What's the chance that the professor will be in a bad mood when he grades the exams? What's the chance that if I go to this party, a certain person that I might want to meet is there? So that's all probability theory, this is a simple kind of probability problem, right? That we have a variable that's normally distributed, and we can then calculate what the probability is because a normally distributed variable is defined, the probability distribution is defined by the mean and the standard deviation, and that's it. So we look at the normal distribution curve. The normal distribution curve is defined by the mean, where it's centered, and its spread, which is the standard deviation, or the variance, right, which is the square root of the standard deviation. And the question we're asking is, what's the probability that we'd observe this random variable to be of value 180 or less? In other words, what's the area under the probability distribution curve defined by that area here under the probability density function below 180. So what's that probability? Well, we can look that up in R with the simple command pnorm 180, mean 200, standard deviation 50, and we find that that probability is 0.34, so it's 34%. So this probability is 0.34, which means that this probability, the black shaded area, is 0.656, right? 1 minus 0.34. So this is 1 minus 0.344. So this is the probability of observing x greater than 180. Right? So that's how we use the normal distribution to assess the probability of an event for a variable that is randomly distributed. And we are assuming in this case that it's randomly distributed. Not all variables, not that it follows the normal distribution. Not all variables follow the normal distribution. Our second use of the normal distribution is when we have a hypothesis about the mean of some variable for a population. So we might have a hypothesis about the height of people in a population. Our null hypothesis, for example, might be that their height is 68 inches. Our alternative hypothesis is that their height is not 68 inches. So we're talking about the average height for a population. We take a sample from this population. And as long as the sample size is large, we'll just say informally that means as long as it's greater than 100, we take that sample, we calculate the mean height for that sample and the standard deviation of height for that sample, and then we calculate this statistic that we're going to call the t-statistic, a t-stat for short, which is the mean height minus our null hypothesis of what the height for the population is, divided by the standard error of the mean And the reason we have a standard error for the mean is because this mean that we've calculated, this average for the sample, would be different with different samples. And so the mean itself, we treat that as if it were a random variable, because the mean could take on different values depending on the sample. If we had a different sample, we'd get a different mean. And so this t-stat is the ratio of two random variables. This is a random variable, and this is a random variable. This is a number, our null hypothesis. And so this t-stat has a distribution. And we can show, Chapter 2, Math 8, almost 40 showed that this estimate, this t-stat, this statistic, follows the standard normal distribution. So we're not going to prove that here. We just know that it does follow the standard normal distribution. And so the probability of observing a t-stat of the value that we do observe, then we can just calculate from the standard normal distribution. And for example, if in our sample we observed a mean height of 64 and our null hypothesis was that the population height was 68, and assumed that the standard error of the mean was 0.4, so the standard error of the mean we get from the standard deviation of the sample and the sample size, let's say it was exactly 100, the standard error of the mean then is defined as the standard deviation divided by the square root of the mean. So that gives us the 0.4. So that's where the standard error of the mean, this is an x, I think we're calling it, variable. So that's, again, in Chapter 2, Chapter 3 of Stock and Watson. So in this case, we get then a t-stat of -10, and we can go and plug into R what's the probability of seeing a t-stat that far away, or that large. In other words, seeing a sample mean that far away from the null hypothesis mean. So our null hypothesis is that the mean is 68. We observe a mean of 64, which is divided by the standard error of that mean, which defines sort of how many standard errors are we away from our null hypothesis. We usually do these tests as two-tailed tests. That is, we think how far away on either side of the null hypothesis are we, and if we're too far away, if the probability of being that far away or greater than that far away, if that's very low, we'll say that our null hypothesis should be rejected because it's so unlikely we would observe a sample mean as far away from the null hypothesis population mean that we should reject our null hypothesis of the population mean. So we calculate the t-stat by, the probability, the p-value, is equal to 2 times the probability of being in this tail, so p norm minus the absolute value of the t-stat, and then we multiply that by 2 in order to get this tail. So in this case, we have 2 times p norm of -10 with mean 0, standard deviation 1, because it follows, the t-stat follows the standard normal distribution, and we see that that's an incredibly small number, e to the -23, and so we reject the null hypothesis. That's our second use of the normal distribution. Our third use is, suppose we want to compare two sample means. So we have 2 samples from 2 populations, the population of females, the population of males. We have null hypothesis that the males are the same height, let's say, as females. That's our null hypothesis. So we want to construct a t-statistic analogous to the one we just did. The t-statistic here is that the difference in the sample means shouldn't be or we're measuring our t-statistic as how far away is our sample difference in means from our null hypothesis difference in means. Our null hypothesis difference in means is that the means are equal to each other, so that the difference in means is 0. We have a sample where we actually calculate a difference in means. We can calculate what the standard error is of that difference in means, and the standard error of the difference in means is given by this formula, again from Chapter 2. So we go ahead, and then that t-statistic follows the standard normal distribution, so we can calculate what the probability is of observing a sample difference in means as far away from our null hypothesis difference in means as we observe. If that probability is very, very low, we should reject the null hypothesis because we're observing something that has a really low probability, so it's more likely that our null hypothesis is wrong. And finally, our last usage of the normal distribution so far is when we're estimating a regression coefficient. We have a sample, we estimate beta 1 hat, we have a null hypothesis that beta 1 is equal to 0, so we construct a t-statistic of the difference between our estimated coefficient beta 1 hat, our null hypothesis of beta 1, and divide, as usual, by the standard error of beta 1, because the beta 1 that we've estimated, beta 1 hat, is a random variable, because if we'd had a different sample, we would have had a different estimate of beta 1. So we construct our t-stat. The standard error is given by the formula in the book. We can usually assume heteroscedastic error and thus calculate easily what the standard error is, and that follows the standard normal distribution. So we can look up what the probability of observing a coefficient of the magnitude we observe and a standard error of that coefficient. And if that probability of observing that is really, really low, so p is less than 0.05, we reject the null hypothesis that beta 1 hat is equal to 0. So those are the 4 times we've seen the normal distribution so far in econometrics.